UVVis, or the ultraviolet, and the mass spectroscopy are a very minor portion of what we're going to talk about. IR is a lot larger. We've already kind of had a discussion on that. And NMR is also a lot larger. The mass spec and the UVVis are more important for like industry, which arguably that's where most of you would be going anyway. Very few people would actually be going into a research academic lab. So we should really be spending more time on mass spec and UV. Unfortunately, that's not the way the curriculum is built. It's designed to talk about things that an academic would need. What does an academic need? IR and NMR. Okay? So just be kind of aware of that issue. When we look at chapter 15, IR and UV, what we're referencing is the electromagnetic spectrum. It's kind of our big summary of it. And within that electromagnetic spectrum, we have a bunch of regions that we've labeled out with their corresponding wavelengths and all that fun stuff. Okay? The thing that is important is that we can then fire these different energies at molecules and see how they respond to those said energies. Okay? That response can give us some information about what's there. Okay? So when we're looking at UV, we're talking about electronic transitions, exciting an electron from the ground state to an excited state. Okay? That gets us information about the energy of our electrons. What's the most likely electron that I would excite? I like where valence is going. Valence works great for atoms. We're now looking at molecules, so I don't accept valence.
Non-bonding?
Non-bonding, not necessarily.
Pi bonds.
Pi bonds is better, but also not necessarily. When we talk about valence, why are we talking about the valence electrons? What are we ignoring when we talk about the valence?
Whatever's on the inside.
The inside, we're ignoring the core electrons. So when we're talking about electronic transitions, what electrons are we most likely to excite in a molecule?
The one on the outside of the molecule.
The one on the outside, because they would be the,
Farthest out.
well, we can accept farthest out, highest energy. Where would those electrons be located? Where are all electrons located? In an orbital. If I'm looking at the highest energy electrons in a molecular orbital, I'd be referencing the highest occupied molecular orbital,
Yes.
the HOMO. When we're looking at ultraviolet light and electronic transitions, we're talking about taking an electron from the HOMO orbital and moving it to a higher energy orbital. Which higher energy orbital is going to be the easiest to make that jump?
Lowest unoccupied.
The lowest unoccupied molecular orbital. So when we talked about molecular orbital theory, this is where ultraviolet comes in. We're talking about that transition. That transition happens to match the ultraviolet light for compounds containing pi bonds. Okay? We can get electronic transitions happening in other areas for sigma bonds, but that tends to happen outside the UV range. We're outside the useful UV range, and so we don't really discuss those. Okay? As we move lower in energy, we can move into the infrared region, and in the infrared region, we're getting molecular vibrations. Not enough energy to cause the electrons to jump orbitals, just enough to cause them to wiggle. We can detect that wiggle and correspond that to the local environment of where the electron is located, hence bonds. So IR gives you information about bonds because we can see the electrons wiggle in that area. After that, we can move into rotational motion with microwave. We can also go all the way down into radio waves to do nuclear spin transitions. So when we're talking about NMR, we're talking about causing the nucleus of a magnet to change directions. Okay? We can do that with radio waves. Okay? So each of the forms of spectroscopy are ultimately using some form of energy. Okay? It is how our molecules respond to that energy. I left mass spec off by accident. Mass spec is we explode the molecule. In the process of exploding it, we make ions. We're looking at mass spectroscopy. Typically, we're using very high energy particles to cause it to explode. Okay? So, UVVis, We could talk about Beer-Lambert law. I don't want to deal with it. Ultimately, what we're looking at is an absorption spectrum. You should be familiar with this from 152 because you ran labs dealing with this in 152, theoretically. Okay? We take a scanning of the wavelengths, usually UV, up through the visible range. And all we do is see what happens. Does the light pass through the sample? Okay? If it passes through the sample, how much light was absorbed? None. So we get a 0, and we just get a flat line. If our compound does interact, for instance, if it has an electron, a HOMO to LUMO gap that happens to match the energy on that from 200 to 800 wavelength, we would see a peak. Okay? Because our orbitals aren't perfectly stacked out as energies, we get a slight spread to it, and we see kind of a breadth associated with that peak, because there's a variety of transitions that could happen within there. Don't stress about the details on that. Okay? UVVis typically centers on pi bonds. So if a molecule has a pi bond, we expect to see something in the UVVis spectrum. The more pi bonds, possibly the more we would expect to see in the UVVis. Okay? That possible has to do with the characteristics of those pi bonds. Okay, so there's our HOMO-LUMO gap. What happens if we conjugate those pi bonds? So when we start at the far left, we just have a single pi bond. Move to the middle one, 2 pi bonds. But those 2 pi bonds are conjugated with each other. Okay, that means the molecular orbitals all interact, which means we get 4 molecular orbitals. What happens to the gap between the HOMO and the LUMO? It shrinks a little bit. So as we increase conjugation of the pi bonds, the gap between there gets smaller. That gap corresponds to energy, which means I get lower energy light causing the excitation. So I would see a signal at a lower energy. What wavelength would a lower energy be? A higher wavelength, because of the inverse relationship between energy and wavelength. Okay? The more pi bonds we get, typically the more we shift out of the UV and into the visible. That's why when we refer to ultraviolet spectroscopy, it's usually referenced as UVVis. Vis for visible. If we think about the colors that we see in clothing, most of those colors are due to pi bonds in organic molecules. That's why we see color, is because of organic chemistry. Okay? It is those particular molecules and their conjugation that causes the gap between the HOMO-LUMO to match perfectly with a particular wavelength, removing that part of the visible light spectrum from what we can see. Okay? Because it's been absorbed by the molecule. Increased conjugation, you increase or you decrease the gap between them. And that's what this is trying to show. Okay? So let's look at a slightly different molecule. Same concept as this one, 2 pi bonds. But now I'm going to do that. Do those pi bonds talk to each other? No, their molecular orbitals don't interact, which means I really have 2 independent pi bonds. If I was to go through and look at the molecular orbital diagram, I'm going to have a HOMO and LUMO for the red one. I will also have a HOMO and LUMO for the blue one. Have I changed the energy gap? No. So what happens to the wavelength of light causing or getting absorbed by this molecule? It stays roughly the same. I don't see a change in it because I haven't changed the energy of the orbitals. The only way the orbitals change energy is when I can get them to interact with something else. Because we're talking about pi bonds, we need to look at p orbitals. Okay? We can see this if we go through and look at a table. Let's just pick a quick one to look at. Okay, there's 1 pi bond, there's 2 pi bonds. What happened to the energy of light, the wavelength? 177 versus 178. There's hardly a change at all in it. There's a little bit of a change because the atomic orbitals have changed a little bit, but I haven't really affected the pi bond. If instead of having them away from each other and I now bring them close enough to each other where they can do resonance, what happens to the wavelength? I now get a significant change in that wavelength. And notice it goes up. Why does the wavelength go up? Because the energy is what I want to be referencing. The energy between the HOMO and the LUMO has now shrunk, okay, due to that conjugation. That's all we're talking about. Okay? You will hear reference to something known as lambda max. What is lambda? Wavelength. What is max? Maximum. Okay? So what we're talking about with lambda max is where would I expect, what wavelength would I expect the largest absorption? That's it. Okay? Depending on the molecule, I might see multiple different peaks. Okay? Those are going to correspond to different transitions. Okay? But the largest lambda max, if I can now compare across structures, is going to happen because I have increased conjugation. It's going to shift to higher and higher wave numbers or lower and lower energy. Kind of, sort of. Okay? Active area of research, solar cells, and the reverse of solar cells. Like the reverse of solar cells. We don't do that. What does a solar cell do? Absorbs light to do what?
Cause energy.
To create electricity. What's the opposite of that?
Consume electricity.
Consume electricity and
Create light.
create light. We don't have any instruments that do that. LEDs. LEDs are effectively the same thing. They're doing the opposite of what a solar cell does. We pump electricity in, and we want that electricity, when it goes to a lower energy state, to emit light. Okay? Solar cells are doing the opposite. We hit it with light and hope that causes enough of a jump to get the electrons to jump up. We're talking about the electrons jumping different orbitals. What orbitals are they jumping? The HOMO and LUMO. They aren't for organic molecules because organic molecules aren't as stable as, say, inorganic materials. So if you were going to move into an inorganic chemistry class, what they're going to talk about is HOMO and LUMOs, except they call them something else. The conduction band and the valence band. The valence band being our highest energy electrons, and the conduction band, the electrons that are allowed to move because they've jumped up to a higher energy. Okay? So that gap dictates UVVis. It also dictates solar cells. It also dictates LEDs. Okay? It's just a slightly different spin on the system, and because somebody else is studying it, they come up with different names for it. But it's ultimately the same concept. Okay? So, you can tell already how important UV is to us. You're like, what do you mean? How can I tell? We are literally done talking about UV. That's it. That's all I wanted out of it. Okay? Lambda max tied to conjugation of the pi bonds. Okay? That's about it. The IR region. Okay? In the IR region, we could look at wavelengths as well. For whatever reason, we decided to not go based off of wavelength, okay, or frequency or energy. Why? I don't honestly know. Okay? My best guess is that we're trying to differentiate the different forms of spectroscopy. Okay? So we're using a different axis so that when we look at an IR spectrum versus a UVVis spectrum, we can very quickly say that's UVVis and that's IR. If they were both looking at wavelength, well, how would we know which one was which? Okay, we'd have to do a little bit more interpretation. Okay? So when we look at our x-axis for IR, okay, we're looking at what's known as the wave number. Okay? The wave number is related to the frequency. It's 1 over your wavelength. It's not exactly the frequency. It's similar to it. Okay? I don't want to get into the mathematics of it. I don't understand it. That's just what it is. Okay? We got our energy thing there. We're looking at waves. Okay? Our energy increases, frequency increases. Our wave number will also increase. So we're now seeing a nice direct relationship. What's on our y-axis? Absorption wouldn't be a bad idea, but we've already kind of used absorption somewhere else. So we use transmittance. We're like, well, what's the difference between absorption and transmittance?
They're the opposite of each other.
They're just the opposites. Absorption is that the light was absorbed, right, and I see a peak. Right? For percent transmittance, what we're going to be seeing is now valleys where it was actually allowed to pass through the sample or not allowed to pass through the sample. Why was it not allowed to pass through the sample? Because it was absorbed. Okay. Why did we do it that way? Again, I don't know. It could very easily just be because, well, we can now very clearly see a difference between UV and IR. UV is going to get us nice peaks because we're talking about increasing the absorption. Okay. In IR, we're talking about percent transmittance, so we'll see valleys that then get referenced as peaks. Okay. Those peaks just happen to be in the negative direction from our frame of reference. Okay, kind of makes sense? Okay. When it comes to IR, there are some things that we could look at to kind of draw kind of parallels. So if we look at similar bonds, so if we say C to H, C to D, what's the difference between C to H and C to D? Right, they're both carbon and hydrogen. What is D?
I don't know.
Probably heavier than hydrogen.
What is D?
I don't think D exists.
It does exist. Really? Nobody's heard D before? Do. Can you get the rest of it? You've put out all the possible aspects to this that actually work. D is deuterium, which is heavy hydrogen. It just has an extra neutron. It actually has a neutron. That's it. Okay? Which means when we transition from carbon to hydrogen versus carbon to deuterium, all that's changed is I've made one of the atoms heavier. That's it. Okay? What happens to the frequency at which it shows up? So we go all the way across 3,000 to 2,100. It decreases. Okay, so if we change the mass of one of the atoms, it's going to change the energy with which that bond vibrates. Okay, which is kind of the key point in IR. We're talking about bonds vibrating. That's it. Okay, this could get really dicey. Let's be careful. Think about your answer before you start shouting something else. What things vibrate? Fair enough. Bonds, we already said that one. Outside of the chemistry classroom. Slinky, thank you. Okay. Bullet dodge. Springs or slinkies, okay, they have a vibration. Okay. If I attach a small weight to each end of that spring and then I stretch it apart and let go of it, it's going to vibrate with a particular frequency, okay, or an energy. What happens if I change the mass of one of those and then do the same thing? Am I going to expect a different frequency of the vibration? Yeah. Yes. What is a bond? A spring. Okay? So when I change the atoms of the bond to different masses, I expect a different frequency of that vibration. That's all that's really happening. Okay? What happens if I jump to a double bond? I have two springs. Is that going to change the energy that I need to put into it to cause it to vibrate?
Yeah.
Yes. Okay? And so we can see that in the next one. Single spring, double spring, triple spring. What happens? I go from a lower frequency to a higher frequency. Do I have to put in more energy to cause a triple bond to vibrate? Yeah, it's holding tighter. It doesn't want to stretch. So I have to put in that more energy to cause it to vibrate. Okay? That's what this slide is attempting to go through and show. Okay? And the textbook addresses things like this. It's a minor nuance, and we'll encounter kind of repercussions of it with, heaven forbid, resonance. Okay? what might I expect to happen to the energy of that bond? The carbon-oxygen bond. Should it show up at 1700 like the textbook suggests here? Why not? It's complex, so it should change. Good. Okay. I've added an extra atom to it, which could potentially affect it. Does adding any atom change the bond vibration?
No.
Yes. Okay. This is what makes IR a little bit tricky to analyze, because you see all these numbers and you're like, well, it shows up at 1710, so that can't be a carbonyl because that says it's 1700. It's a load of freaking crap. As soon as you throw on a different atom, you're going to get some shifts. How much it shifts can be challenging to deal with. So when you look at IR, the description that I gave in the past, you've seen those little shape boxes for, little babies? They have to take the circle and they put the circle into the circle hole and the square into the square hole. That is literally what IR is. Don't pull out the tape measure to measure the size of the circle hole and the size of the circle piece you're trying to put in it. Okay? That's the wrong approach to this. Does it fit? Yes. Good. Move on. So your IR interpretation should be fairly quick. You should not be getting into the nuances and the weeds of the numbers. When we get to the numbers, what we can be saying is how would I expect it to change? Okay? And that's the next question here. Okay? Nitrogen isn't just any atom. What is special about that nitrogen?
It has a lone pair on it.
What could that lone pair do?
Create resonance that
It could resonate in, but then I would exceed the octet on the carbon, which means push it up there. Which means for this structure, is there always a carbon-oxygen double bond? No, it's actually a carbon-oxygen single bond, which means it's going to shift to slightly lower frequencies. So we can predict what resonance is going to do to some of these by looking at how it affects the bond characteristics. You had your hand up for a long time. And
yeah, that's what I was going to talk about. Like,
yeah.
Is that what the resonance is doing?
Yep, that's what the resonance can do. Okay? It is not always straightforward. It is not always easy. Okay? If you see a question that is forcing you to talk about that, then do so. Okay? If the question doesn't force you to look at that, then don't look at that and just say, does the shape match? That's all I want you to get out of it. Okay? The next kind of big complexity or issue that can pop up with IR is that IR is talking about dipoles. Okay? When I stretch that bond, that spring, what I'm looking at is it stretching asymmetrically. If it stretches perfectly symmetrically, guess what happens? It cancels out. If it cancels out, there is nothing to see. So when we're talking about the stretching frequencies in IR, they must have some kind of asymmetry to them. Okay? That's why when we look at our tables back here, we see a lot of different atoms show up. Carbon, hydrogen, carbon, deuterium. We'll skip that for a moment. Carbon, nitrogen, carbon, nitrogen. Okay? The larger that dipole, that difference in electronegativity between those individual atoms, guess what happens? The more intense the signal becomes. Okay? That's why when we look at an OH bond, okay, or a carbon-oxygen double bond, we see very intense signals. Okay? Why? Oxygen's really pulling on those electrons. We get a huge dipole so that when I cause that bond to vibrate, I can really see it. But if I look at a carbon-hydrogen bond, what happens?
It's not that strong.
It's not as intense because the difference in electronegativity isn't there. Okay? So why can I see carbon-carbon single bonds or carbon-carbon, let's not talk about the single ones, which we'll address here in a second too, carbon-carbon double bonds and carbon-carbon triple bonds? When we look at those, if I looked at a molecule that had a carbon-carbon double bond, what do you think might be an example structure I would draw?
No.
Would I see the double bond? Is that structure symmetric? No. What does that mean? I will see it. Okay? So as long as there's asymmetry, I will see it show up. If I was going to look at a triple bond, would I see the triple bond?
Yes.
Yeah, there's asymmetry here. How about now?
No.
No. Cancels out. So what happens to the signal for the carbon-carbon triple bond? Non-existent. It disappears. This really happens for the triple bonds because the triple bonds have that massive line asymmetry because they're linear. Right? The carbon-carbon double bonds, it's less frequent because there's now 4 potential positions. All I have to do is change one of them and the whole system becomes asymmetric and I now see a signal. Right? So what can potentially show up is this issue of IR inactive bonds. Any bond with a 0 dipole moment, okay, does not show up in the IR. Okay? Acetylene is a potential example for that. That's the one with the triple bond here. Why would you expect to not see that as a potential answer or a potential question? What is the phase of acetylene?
Yes.
It's a gas, welding and all that fun stuff. Okay? How many gases have you worked with in the lab?
No.
Oh, they're not easy to work with. So you're probably not going to be tested on something that you don't get exposed to. Add enough carbons to it, it can gain enough London dispersion forces that now it can transition into being a liquid. Right? I don't know if this one's a liquid necessarily, but let's just say it is. Do I expect to see the triple bond?
Yes.
Why?
It's no longer symmetrical. There's an asymmetricality.
There is an asymmetricalness to this. How asymmetrical is it? Just a little bit, which means how intense should that peak be?
Not very.
Not very intense. Okay? So the intensity of the signals that you pick up have to do with the symmetry in the molecule. The more symmetric the molecule, the less intense the signal gets. Okay? So be kind of aware of that when you're looking at things. I tend to not test at that level, but it could show up. Okay? So if we look at something like this, we now have an IR spectrum that we could evaluate. Okay? And you should be very quickly telling me that there is
SP3 hybridized.
CHSP3 and then be done with it. Okay? That is not because there are 1, 2, 3, 4 peaks. It's that this peak shape with all of those peaks roughly matches what I would expect to see for a CHSP3. How do I know that?
It's south of the 3000 mark.
Because I've looked at enough spectra with CHs where the carbon is sp3 hybridized. IR spectroscopy is about shape matching. Why do babies suck at putting those shapes in the boxes?
They don't have experience yet.
They haven't had the experience with those shapes. If you attempt to go through and just memorize that circles are this size, you're going to have a hard time with IR spectroscopy. You need to be getting the practice of trying to jam the circle into the square hole to realize it doesn't fit. Okay? Which sucks, kind of, for you, because you have to get that practice. But the nice thing about it is once you have that practice, if I asked you to put the circle in the square hole right now, you'd be like, no, that doesn't fit. You would know that relatively quickly. So your IR spectroscopy is something that should happen very, 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 very fast. You'll also notice that there's a bunch of peaks out here. I didn't label those. Why not? Where's the fingerprint region? Actually at 1400. Okay, that's a horrible straight line. This is known as your fingerprint region. Okay, it's what identifies the molecule. You could identify me by taking fingerprints of me. It's not easy to go through and do that process, but you could do it. Same thing with our organic compounds. It's not worthwhile for you to go through and identify something based on the fingerprint. If you moved into industry, sure. Okay? And even then, you aren't going to do it. what are you going to do? You'll tell a computer to go match the spectrum you just obtained to a library of possible compounds. Okay? So you don't have to stress about the fingerprint at all. There is this peak in here. Okay? Some people said 1500. The fingerprint region is ultimately kind of arbitrary. It just depends on the individual textbook and the person. Okay? I'm pretty sure 1400 is the lowest I've ever heard referenced. I have started to see 1500 show up more and more. Okay? So what you could do is theoretically ignore anything in that fingerprint region. If you want to say it's 1500, by all means go ahead and do so. For me, personally, my fingerprint region goes up to about 1600. Maybe even 1650, depending on my mood. Okay? That wasn't supposed to be a joke. Okay? Why? There's a bunch of stuff that can show up between 1700 and 1500. Okay? Or 1700 and 1400. There's so much stuff that could show up in there that more than likely I'm going to screw up the analysis. So unless I am forced to look in that range, I'm not going to. Okay? So I treat that entire section as fingerprint and effectively block it out. Okay? I don't entirely ignore it because there is information in there. This is why when you see the IR spectra, you don't see me delete that section of information. I want you to know that there's information there. You just may not be responsible for going into it. Make sense? Okay. Oh, yeah, see, that was an accident. So just pretend that didn't happen. Major regions of the IR spectrum. Okay, so you can see the 4,000 to 2,500. Okay, those are all pretty much your single bonds, okay, to hydrogen. So you're looking carbon, nitrogen, and oxygen, all kind of falling in that range. Okay, then you get this dead zone between 25 and 2,000. Okay, that dead zone really only corresponds to triple bonds. Okay, so more than likely, what will you see through there?
Nothing.
A nothing. It's a flat line. Right? They just move straight through and we don't see anything show up. If a peak shows up, it's a triple bond. Okay? Then from about 2,000 to 1,500 is where you get your double bonds. Really all I look for is the carbon-oxygen double bond. Okay? That one is hugely asymmetrical, very intense, jumps right out of the page at you. Okay? Then after that, I kind of just ignore the rest of it, because that's all now into the fingerprint region. Is there information there? Yes, absolutely. You get your single bond stretches, and then you can get bending modes. Okay? When we talked about IR, we're talking about a vibration. Okay? My arm can vibrate this way. Okay? It could also do this. That's it bending. Both of those are forms of vibrations, which means there's a signal for them in the IR. You're not responsible for digging into it, but you might see those things pop up in your textbook or in future chemistry classes. Okay? I usually like to throw this one out there too. There's actually a name for it. I don't remember what it is. Okay? But there are larger than textbooks of these kind of things. If we go through and actually read this, for alkanes, right up here at the top, we expect to see an S signal and an S signal just under 3,000. What does that correspond to? The CH of a methyl. Okay, I would also expect to see an M signal and an M signal. What is S and M? What does S stand for? Strong. What does M stand for? Medium. Okay? Or moderate. I'm actually not even really sure. Okay? What they're referencing is the intensity of the signal. Okay? So they're saying if you see some strong peaks showing up just under 3,000 and some strong peaks right around 1,400, you likely have a methyl. Cool. Okay, that's actually useful. What's the one right underneath it? For those of you having a hard time seeing, I literally underlined the exact same areas, but now it's a methylene. Is this useful?
Not terribly.
Okay. I would see the exact same signals for a methyl versus a methylene. Okay. How would I know which one's which? I wouldn't. That's why this is a dumb table to use. Okay. This is why what the textbook shows you is a little bit nicer. Oh, come on. Oh, did I actually delete my lists from this? I did. Oh, well, that's unfortunate. That's why what the textbook shows you and the summary slides that I think I put up for IR spectroscopy go through and they list out and say for a CH where the carbon is sp3 hybridized, it is less than 3,000. And OH typically shows up 33 to 3,500. 36. There's a lot of gray area. Okay. This one I usually add and say that it's broad. This one I would say is sharp. Okay. The NH. Pretty much the same thing, 33 to 3,500. That makes it difficult to distinguish those. Okay. It's not as broad. Well, what's not as? Okay, a smaller amount. Am I smaller? In comparison to Shaq, yeah, I am. Okay, so that comparison is all really ballpark. That's why I don't recommend even using that. What you should be using is the list of bonds and saying, what should I know? Which bonds should I know how to identify? Now I need to go out into the world and I need to find bonds that represent that, or signals that represent that. OH, NH, CHSP3, CHSP2, CHSP. I don't know why I threw another parentheses in there. CH from an aldehyde. A triple bond, I don't care if it's to carbon or nitrogen. Carbon-oxygen double bond. Okay? I want to be able to identify those. That means I need to go out and I need to find spectra that match those. Okay? So that I can see them. That's what the textbook tries to do. That's what the supplemental online IR video tries to do. And what the IR Solve stuff tries to do. Okay? You need the practice with those shapes. Mash the shape into the square hole a couple times, find out that it doesn't work. Okay? Okay. Regions. This again just kind of draws attention. We're looking at here a stretch. Scissors. There's a scissoring action as well as a vibration, believe it or not. A rocking after the exam, right? Okay. And you can potentially get bending actions happening out there. So you may hear reference to these other types of vibrations. Don't stress necessarily about those names. Okay? Just be aware they're just talking about the different vibrational modes that you could see that would potentially show up. Kind of make sense? Okay. What do we see in the IR? CHSP3, carbon-oxygen double bond. Somebody see something up here? Doesn't really look like an NH, doesn't really look like an OH. Guess what that one is? Whoa, that didn't make any sense. Where's the carbon-oxygen double bond supposed to show up? 16, 15, 1800. What the hell is showing up there? That's a carbon-oxygen double bond. That carbon-oxygen double bond is so intense of an absorption that guess what it does? It can absorb 2 photons of energy, okay, of a lower energy to match that absorption frequency. Carbon-oxygen double bond shows up here about 1,700. Okay? If I double the energy, what would I be? 3,400. Holy mother. It's known as the carbonyl overtone. Right? It's one of those kind of subtle things that you wouldn't see until you had enough practice looking at them. I'm sorry. That's about all I can tell you. Things like that show up in a couple different areas. What I would argue is that doesn't match the shape of the OH, that doesn't match the shape of the NH. If it doesn't match the shape, then I don't know what it is. Don't worry about it. Okay? Do the stuff that you do know something about. Okay? If you really feel like, no, that's important, I've got to label it as something, then put something in there. I think it's an OH. When I write OH like that, does that mean I think it's an OH? No, what does that mean? It is an OH. So that's a horrible way to write this. What can I add to it to make sure that if I go back and look at this later in the exam, I know I'm thinking? So if I later go back and find out that there's no OH, I can be like, oh, I don't know what the hell that was. I could even go through and put a line through it. As a grader going through, and if I see that question mark, I'm going to be like, you shouldn't have said that. Oh, you put a question mark. Okay, you just didn't know. That's cool. Okay, that does not mean you should be putting a question mark next to everything. Right? Because then that means that you don't know anything about it, and of course I'll take off points. Okay, so you do need to prove some things. That's why I just wrote out that list of those important bonds. Okay, what do you see? Is a good stop. Okay, there's my line at 1650. I'd say I'm not going to touch this until I have more information. Okay? Since when we hit the next button, it all disappears. I don't have any more information. What do we have? Okay? This is CHSP2. These are CHSP3. Seriously, how do we tell the difference between that? On an exam, it kind of sucks. Is there a ruler up here? Okay, so here, we'll demonstrate on the board. Okay, hopefully I don't break anything. On an exam, it may be difficult to see that line. You do have another sheet of paper. Take that sheet of paper that has square edges, line it up like a ruler. Ouch. Right there. Where's that leftmost one?
North of 3,000.
Just higher than 3,000. I know that is CHSP2. So you may not be able to see that line super clearly. Take advantage of your exam. Take it apart, put something down so that you can see that. You want to bring in a ruler, bring in a ruler. I don't care. Okay? But it can be difficult to differentiate the CHSP2s from the CHSP3s. It really hits that line at 3,000. Okay? Very rare exceptions. Do you get CHSP2s dropping as low as 3,000? And very rare exceptions, do you get CHSP3s going higher than 3,000? Okay. After that, what do you see? Okay. I remember 1650. I would say I'm not going to worry about it unless I have more information. Do I have more information? I have a carbon that is sp2 hybridized. If a carbon is sp2 hybridized, what does it likely have? A double bond. I now have enough context to be like, yes, maybe I can venture into that, and that this peak showing up at 1600 could be due to the carbon-carbon of a double bond. Okay. Add to that, if I dig back far enough in my memory banks, the carbon-carbon of a double bond shows up at 1650. That's showing up at 1600, so it's a little low. It's a little low because resonance in the ring, causing the pi bond to weaken just a little bit, which means the bond shifts to lower energies. There's our 1600. Because the aromatic ring has all those other things in it, it can bend and flex a little bit. It also picks up some peaks down here. All of those are now in conjunction, carbon-carbon double bond, aromatic. What you should be labeling it is the carbon-carbon double bond, not aromatic. Why?
Because you can't really tell if it's an aromatic one. You're only getting carbon-carbon double bond from this.
What is an aromatic? It is that benzene structure. What bonds are in a carbon or an aromatic structure?
Singular double bond.
CHSP2s. You're telling me by calling that, if I just labeled that aromatic, there's a CHSP2 in there? No, it's over here. Okay? So what you should do is identify it for what it is. It's a carbon-carbon double bond that belongs to an aromatic. It's not an aromatic. Okay? Very subtle nuance and a differentiation between those. IR tells you bonds. If you start labeling functional groups on your IR, I will get angry and subtract points. Okay? You need to tell me the bond that is present. If you want to add more information after that, that's cool. That's on you.
So that's okay?
Yep.
If we wrote something like this.
Yep, because you've identified the bond and then said that meant aromatic.
Okay.
That's an entirely different analysis than just saying aromatic. Last one. That looks kind of hard to tell. I don't feel like pulling out that stupid thing again. I'm just going to call it CHSP3. Looks a little on the low end, but that looks like a carbon-oxygen double bond. Interestingly enough, didn't really double this time. Doesn't always double. That's why we don't always talk about it. Okay? That would be the end of my analysis on that. Kind of makes sense? Okay. That's IR. So we've done 2 forms of spectroscopy in like 45 minutes. Mass spec. Okay? You literally take a car and you blow it up. Let's try that again. You don't take a car and blow it up. You take the molecule and blow it up. The analogy to using this, okay, would be like those CSI shows that come in after a bomb has exploded and they go through and they take all the pieces and they go like, this is where the bomb was, this is who made it because they had this signature on this piece in the... What? A bomb, and you went through and said that it had this component in it. Okay, if they can do that with a bomb, guess what? We can do it with a molecule. That's what we're doing with mass spec. We're CSIing the crap out of it. Okay? Mass spec also typically shows up in CSI. They're like, oh, let me just figure out what's in this. Bloop, boop, 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 boop. Oh, it's composed of dirt that was found in the northwest corner of... Mass spec kind of has the ability to pull that off as long as you have a standard sample on which to compare it. If you don't have that standard sample, you aren't doing that. Okay? Add to that, it's not like boop, 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 and there's an answer. It's like I put it in, and then I go to the bar for a couple days, and I come back. Okay? And now I have an answer that I then have to sit down and analyze to decide what components were in it. Okay? Because what we end up seeing as an end result is whatever was in there. And if you're doing some CSI crime scene stuff, there's probably a lot of crap in there. You have to decompose all of those parts. Okay? Atomic line spectra, you guys remember that? Gen Chem? Okay? Did you guys know astronomers use atomic line spectra?
Yes.
Okay, cool. At least one person did. Okay? Yeah, astronomers use it too. They aim telescopes at suns and stuff like that, and planets, and they can figure out what elements were on that planet.
Atmospheres.
What? Yeah. Okay, what happens is the light coming back is coming from particular elements with an atomic line spectrum. So what they can do is decompose the light coming back into what elements made up that entire spectrum. Okay? You're breaking it apart into the individual pieces. When we look at mass spec, that's what we would see. We would see the sun coming back, and we would have to decompose that out into all the individual pieces that went into it, which makes it very difficult to analyze an impure sample, which is why when we talk about it, our samples are clean and pure. Okay? So, mass spec basic little picture there. We blow it up. It gets blown up into these pieces. The pieces that we decide to analyze are charged pieces, okay? Because we need to be able to come up with some way to sort and organize these. The charged pieces get passed through a magnet and then through a kind of a delay factor. Okay? That delay factor is going to sort those pieces based off of mass. So if you look at, I think, diffusion calculations that you did in one of those Gen Chem classes, where they talk about the speed of a particle moving through something, mass spec. Okay? The heavier the particle is, the slower it moves. So all we have to do is set up a detector at the end of this column and just be like, did anything hit me yet? Okay, oh, something hit me at this time. I'm going to correspond that time to a particular mass. Okay? That's what mass spec does. It's just a histogram. It just records that something hit. Okay? So when we look at our end result, what we will end up seeing is this recorder here with a time axis and the number of impacts. Okay? What's going to change the number of impacts? Am I going to expect to see more parts if I blow up more cars or less cars? More cars. So if I put more sample in, am I going to get more pieces? Yep, I'm going to get more impacts. Okay? Since I want to normalize, what I go through and do is say the one that I have the most pieces of is now by default 100. So when you look at your mass spec diagrams, your y-axis caps out at 100. And only one signal hits, or typically only one signal hits it. Okay? That happened to be the most stable piece. Okay? So when we blow up a car, we don't expect to see individual pieces of the rubber tire. We probably expect to see a whole tire. Why not individual pieces of it? The whole tire is relatively stable, and so when I blow it apart, it's probably not going to disintegrate the entire tire. Okay? So what we're looking at is the stable pieces that come out. What are those largest pieces that probably aren't going to decompose? Okay? The time recording we then translate into a mass. Okay? Officially, a mass to Z ratio. What is Z? Charge. We made them charged particles as they moved through. What we're really hoping for is that we've only provided enough energy to cause one charge, a positive one. Which means when I read this axis, I don't have to read it as a mass to charge ratio anymore. I can read it as mass. Just the mass, because the charge is always plus one. Okay? And now I have a way to interpret all of the pieces that come out of it. Okay? So when we look at it, we ionize, we take our molecule, we fire electrons at it, it explodes. Okay? In the process of that exploding, I've ejected an electron from this structure. It now becomes positively charged. I would expect to see this piece show up in the IR. Is that top piece particularly stable? Why not? I could kind of accept that. Do I have a bond between the carbon and the hydrogen anymore? No. No, that's not a particularly stable piece. So how many of those am I going to make? Not as much. I'm probably going to make a very small amount of those. If we go through, when I fire it, it's probably actually going to break that apart. Okay? This would get me two pieces. Which piece am I going to see? The left piece. Only the left piece because it's the one that's charged. The hydrogen I don't see because it ain't charged. How else could it have broken? Could have broken where we broke the carbon-carbon bond in between. Okay? So really what we're doing is just trying to explode apart the molecule into those component pieces. We could then evaluate what pieces came out and try and restructure it back together. This is the power of mass spec. Okay? It is an insanely useful technique for that. However, you've got a lot of mental processing that has to go into it. Okay? So let's look real quickly at some stability things. Okay? And because we're concerned about mass spec, let's just focus on the cations. Let's ignore the radicals for the moment. Which of those cations would I expect to be more stable? What makes them unstable? The charge. Okay, what charge is it? A positive. Why is a positive unstable? It needs electrons. Okay? So all of those are unstable because they don't have electrons. What would make them more stable?
Taking electrons from something that gives
If
us-
they had more electrons. So one option that somebody will suggest is, oh, I'll bring in another species. If you bring in another species, you're stabilizing all of them equally. That doesn't help. You can only look internal. Where are there electrons in the top structure?
in the bonds.
In the bonds. How many electrons are there?
2.
Try again.
6.
6. The next one. This isn't looking so helpful. The next one. They all have 6 electrons around them.
We can probably take a look at electronegativity difference.
Nope.
No?
What's the next difference? Carbons and hydrogens. Okay? If hydrogen's electrons are already in the bond, I'm going to regret that, oh well. How many extra electrons are around the top structure? None. How many electrons around the next structure? Okay, it depends how you count. How did you get 6?
Assuming that the carbon has a full octet, there's
So
2
carbon
in the
brings
bond.
in 6 electrons as an atom. So we could go through and say it has 6. How about the next one? 12. The last one?
18.
18. Which of those has more electrons to stabilize the positive charge? The bottom one. Guess which one's the most stable? The top. No, it's the bottom one. The bottom one is the most stable. Okay? We have more electrons around that positive charge to stabilize the positive charge, so it becomes more stable. So when we're talking about cation stability, that's what we're referencing. In mass spec, what I'm looking at is expecting to find positive charge on atoms that have more electrons around them. The more electrons around it, the more stable the positive is, the more likely I would see it as a piece in mass spec. Right? You think you guys get it? Yeah? So there's your test. Which one's more stable of the anions? Why is the reverse going to be true? What makes each of these unstable? Too many electrons. So what am I going to want to put near it? I can't put in protons.
Oh yeah, I'm sorry. Take away.
The only thing I can change are the electrons. Do I want more electrons near a negative or less electrons? Less electrons. Which one's more stable? The top one, because there's 0 extra electrons. The bottom one has 18 extra electrons. Okay? So your cation and anion stabilities, and it goes, oh my God, they're inverse. They aren't freaking inverses of each other. Interpret why they're unstable. Evaluate that why, and it's not a memorization thing. Okay? Don't have time, then yes, memorize it. Okay? So, mass spec, we get 5 primary things that I get out of it. The peak furthest to the right, and it's really the tallest peak furthest to the right. So we find the peak furthest to the right, within 3 units of that peak, the tallest peak. That is now the molecular weight. That is known as the M plus peak. M for molecule, and Y plus? It's mass spec. We ejected an electron from it. So it's the molecular weight of our original structure. Okay? That's if we tried to blow up the car and all we did was dent it. Okay? Fair enough, that's possible. Okay, there we go. Okay? After that, we can evaluate the M plus peak itself. If it is odd, then that means there's an odd number of nitrogens. Okay? We can then look for an M plus 2. Okay? What does an M plus 2 mean? The mass has 2 extra units. Why would the mass have 2 extra units? What units is it getting? rhymes with proton, what is it getting? Neutrons. Okay, why would our proton and neutron definitely rhyme? They both end with tron. By definition, they rhyme.
They don't both end with tron.
You may not like the rhyme choice. That's irrelevant. Okay? It's an isotope effect. Certain elements have different isotopes. Turns out, for our sake, bromine, chlorine are the most common ones to worry about. Bromine has two common isotopes. One is bromine 79 and bromine 81. Because their ratios are roughly 50-50, if I take an average of them, I would get the atomic mass of 80. What is the reported atomic mass for bromine?
79.9.
79.9, damn close to 80. Okay? That's because those two isotopes are 50-50. Okay? Chlorine, I've got it labeled as 1 to 3. It should be the other way around, a 3 to 1. Your M plus to M plus 2 is a 3 to 1. Why? Chlorine has two common isotopes, chlorine 35 and chlorine 37. If they were 50-50, they would be equal intensities. They aren't equal intensities. Okay? Chlorine 35 is 3 times as high as chlorine 37. That's because 75% of chlorine is chlorine 35. If you deal with those percentages and calculated a weighted average, a la 130, you get the atomic mass for chlorine, 35.45. Okay? The last one is and it might be, you might actually see a peak at 127, and I could be wrong on that number. I always forget to check. If you have a really huge atomic mass, iodine's probably present. Why? Because iodine weighs 127 atomic mass units. Okay? If I throw in just a single carbon to that, I have a really big number all right out of the gate. Okay? Thank you for doing the math. Okay? So that's what I get out of the mass spec. That is relatively minimal. We can get a little bit more, okay, if we go in and look at fragmentation patterns. The textbook's going to talk about fragmentation patterns. Are you interested in some kind of forensic science aspect where you might do CSI stuff? You should probably dig into the fragmentation patterns a little bit on your own time. Don't do it in the next week because you should be studying for exam 2. Okay? But over spring break, dig into it. It's neat. You can do some cool stuff with it after class. So you can look for how you could evaluate those pieces that came out of the individual molecule. Ultimately, what you're looking for are multiples of 12 because why carbon? What is this class? Organic chemistry. Everything we're studying is carbon-based. That's why we're looking for multiples of 12. Okay? That same process can get used to evaluate that M plus peak. 86. If I have no other information, I don't have an M plus 2, so no bromine, no chlorine. It's not odd, no nitrogen. Okay? It's not large, no iodine. I can get the formula based off of that. Because at this stage, all I know that's present is carbon and hydrogen. 86 hydrogens, probably not a good answer. So what I can do is take 12 into 86. 6? 72? 4? Damn it.
No, wait a minute. It was
7.
Because you'll get 84.
Yeah, 7.6.
Yeah. 6 is probably a better choice because that
We'll deal with that in just a second. This means I can have 7 carbons and how many hydrogens? 2 hydrogens to make up the remainder. Okay? That is a valid formula. Is that a likely formula? No. So what can I do? I can take away one of those carbons to make it a 6. That mass of carbon becomes hydrogen. I can add 12 and I get C6H14. Is that the molecular formula of 2-methylpentane? Yay! And why is that extra cool and I spent all that time? The very next slide is NMR. So we will be doing all NMR on Monday. It is going to be rough. We're talking about some really hard topics in the next sequence of slides. practice, 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 practice. Okay? I can't stress that enough. Okay?